I think it's a good thing, though, that we become more aware. Anyway, so what we're going to do is we're going to finish up this little section here. To recap, what we're doing is we're noticing the behavior of the polynomials based on the factors. And a key word, and I thought about this over the weekend, is multiplicity. Multiplicity helps us. So essentially, everything I'm teaching you, the goal, maybe not this year, but the goal is when you learn about polynomials, you should be able to look at data and go, oh, that's probably could be modeled by a fifth-degree polynomial, and if I do this, 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 and this, you just kind of, in your mind, can kind of see the way the graph will look based on the information I'm teaching you. So one of the things that we need to consider, as we did on all these other sections, is how many distinct factors. So when something is in prime factorization, such as this is one distinct factor, this is another, this is another, this is another. So this one has 4 distinct factors. Now the other thing we need to determine is what degree polynomial will it be? Well, if I multiply all these out, if I multiply this x times this x, which will eventually get multiplied by this x and this x, I have 1, 2, 3, 4 x's. So somewhere in this equation, I'll have x to the 4th power. I'll have x to the 3rd power, x to the 2nd power. I'll have all kinds of stuff. Maybe, I don't know, stuff might get canceled out. But I know for sure there's going to be x to the 4th power somewhere in there because I have 4 distinct factors and each one of them have x in them. Okay? So it's a 4th degree polynomial, so that means it's an even power, right? What does, just use your hands and show me what an even power polynomial looks like. What would the graph look like for an even power? Yeah, it'd just be a U. Somebody did this. It'd just be kind of a U. Now, the only thing that's different is because we have four distinct factors, is that in the middle, it might look kind of like a W. In the middle, it might do some wonky stuff. Okay? And but it is going to come in from the top and go out the top. And so it'll be kind of a U. It might be like a W. Depending on the number of degrees, it might be like a really crazy spring in the middle. You know, it might just go and oscillate. So anyways, let's just fill out the chart and then we'll graph it and see it. And it says what are the x-intercepts? Now that occurs when y equals 0, so we got to set each one of these equal to 0. So the first one's going to be the y-intercept occurs at x equals 0, right? The next one would be, can you tell me the rest? So what I'm doing in my head mentally is I'm setting this equal to 0. And then I'm solving. So x minus 2 equals 0. Or you could think of it this way. What do I plug in for x to make this equal 0? Well, for this one, it'd be negative 2. Yeah. So there's going to be x equals 2. Sort of. What about here? What value for x makes this equal 0? Yep. X equals negative 3. Now, here's the weird thing. Are they going to cross? So that now what this is saying is that this is going to cross the x-axis 4 times because we have 4 distinct factors. Are they going to touch the x-axis or are they going to cross? Now, here's how you know. A tangent, and this is where I feel like somebody's going to get a little confused on this, but maybe not. Tangent only occurs when you have a multiplicity of an even power. See how this has x squared? Sometimes you'll have an x squared up here. That would mean the multiplicity of this solution would be 2. Okay? But it has to be an even multiplicity. That would cause it to be tangent. We don't have any of those. We don't have any of those. So all of these are going to cross. at x equals 0, x equals 2, x equals -2, and x equals -3. Okay? Then it says how many turning points will we have? Now this one's not as easy. Remember, the turning points occur when you go from increasing values to decreasing values. So we're going to have to graph it now. But it would be at most one less than the degree or power. So since this is a 4th degree polynomial, at most I would have 3 turning points. So let's go ahead and graph this. So I'll graph it in the graphing calculator, and then I will zoom in big. So I'm going to have x, and you just plug it in exactly how you see it. X times x minus 2 times the quantity x plus 2 times the quantity x plus 3. And then we're just going to do a zoom standard, see if that fits. There it is. Actually, it doesn't quite fit. So let's zoom out and see how the y. So my y minimum needs to be a little lower. So just go to Window and see where it says y minimum. What do you want to change that to? Sure, we'll change it to 20. And we'll see. There you go. Good catch. Good call. Good guess. Whatever. You did good. All right. So I'm going to make this big and take a screenshot of that bad boy. Yes, you may. And I don't know if I have room to put this on here somewhere. Maybe I do. I'll zoom it in. I'll put it up here kind of tight. Perfect. Look at that. And we'll just draw a little arrow there. Okay. So I'm decreasing, decreasing, increasing, increasing, decreasing, decreasing, increasing. So I've got 1, 2, 3 turning points. Does that make sense? And one thing we haven't done yet, and I'm going to write it this way. This is what we call a local. Let me zoom in. No, that's too much of a zoom. So this is what we call a local. Well, let me write it so you can read it. This is a local min. Now a min is like a valley. So think of that as a valley. It's not the lowest one, right? But it is definitely where there's a turning point. It's a valley. Now if I scroll up, what is this? Well, it's not the maximum, because the graph goes to infinity here and it goes to infinity here, but it's another turning point or a hill, so we would call this a local max or a hill. Okay? Now down here, this is also kind of a local min, but what do you notice about the overall graph? It's actually the global minimum, too. Now, depending on who you ask, some people will say it's a local min, somebody will say it's the global min. it's the global min for sure. But the main thing that I want you guys to focus on in this assignment is that this is where a turning point occurs. Because that's what really matters when you go to model this. If I go and I'm modeling some data and the data looks like this, I'm going to have to figure out how to make it fit this shape. And I'm going to be more concerned with where the hill or valley is. Does that make sense? There's a turning point, and I want to know if this represented a stock market or a stock. If this represented a stock and I wanted to buy low and sell high, I'm going to focus on the mins and maxes. I'm not going to focus so much on the total or global max or min in this scenario. By the way, the global max would be positive infinity. Okay? So when it comes to the local mins and maxes, I would say there's one local max for sure. And you could say two local mins, but really technically it's one, right? And then you could think of the other one as a global min. And the reason I'm saying two is which is not correct, but I want you to focus on the fact that we're looking for the turning points. Okay? That's what I really want you to focus on, is the turning points. And we define those as min and maximums. If you go to take upper level math, you could actually calculate that based on the function. The first derivative gives you the slope or instantaneous rate of change. These minimums and maximums occur when the instantaneous rate of change is equal to 0. And those are the values that we're interested in. Okay. You know what we didn't double check though? Does it cross the x-axis 4 times? It crosses here, 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 and here. We said -3, yep. -2, yes. 0, yes. And +2. Did it cross through the x-axis? Yes, it did. And that's it. That's all we had to do. Okay. Any questions on that? How do you guys feel about this